I was 13 years old when I noticed that the world was populated by fascinating creatures. Girls. After a few months of careful observation, exploration, and discovery, my attention focused on two of them, both of whom had shown signs of interest in me. Katya was tall, energetic, smart, quirky, and challenged me. Chrissy, on the other hand, was short but glamorous, loving, considerate. She inspired me. It was a very difficult choice. How could I decide? And for those guys out there just now thinking, you should just have dated both of them. No, they were sisters. So that was just not an option. I had to pick one. So I did what any young boy would have done. I went for the looks, and Chrissy became my first girlfriend. And of course, that did not last very long. Now here's the underlying lesson from Katya and Chrissy. Decisions are complicated, but there is a system to them. I clearly gave too much weight to some bits of information. I went for the looks. And I also ignored some other bits that were important, like the fact that Katya and I had very similar tastes in music. So, our conversation today is precisely about this. How do we make choices? And by how, I mean really how, deep down how. What mechanisms does the brain use to weigh the pros and cons of different alternatives? How is it that the electrical signals emitted by each tiny brain cell, a neuron, among a storm of electrical signals, make a person more likely to favor one option over another?
So how is it that the signals from one particular cell get heard and participate in my decision one way or the other? Now, of course, these are very difficult questions and fundamental questions to ask. So how do we even approach them in the laboratory? Well, there are three key ingredients to do this. The key is to simplify the problem, to strip it down to its absolute essence, which is the conflict between alternatives. So in the laboratory, my colleagues and I make three key simplifications. The first one is that the actions that we study are very simple. They are just eye movements. Now, this sounds a little bit boring, maybe. So why do we do this? Well, see, the thing is, we make eye movements about 3 or 4 times every second. So that is by far the most common choice that we make. You know, deciding where to look next is the choice that we make most often in our lives. So what we're trying to do is, instead of looking at a very complex decision that may take, years or months to unravel, like deciding, whom to date or what profession to choose, we look at these very simple choices that occur very fast. So that's number one. The second simplification is that we use very simple objects, a triangle versus a square, or a green dot versus a yellow dot, for instance. And the third key element of our experiments is that we require very fast responses, lightning fast. And that's what makes our choices special. And we call those urgent choices. So our colleagues and I in the laboratory have a bunch of equipment, a special camera that is used to track our participants' eyes at every moment, so we know exactly what they are looking at, when, and where. Now, I don't have this with me today, but I can give you guys a feel for how these experiments proceed, how, what the tasks are, sort of in a simulated environment. So the first thing we should do is go through one of these trials in our task in slow motion. So let's pretend that you are participating in our experiments. Then your job is to look straight ahead at the green dot, first of all, and keep your eyes locked on it. Then once the green dot disappears, this is your go signal, and then you have to move your eyes right away to one of the 2 gray disks. Now these will turn to a different color. One will turn yellow and the other one will turn green, and you never know which side is going to be which. But there's a difference between the green and the yellow. If your eyes land on the green, you get a larger reward than if your eyes land on the yellow. But you have to be really, really fast, because right away, the dots will turn red. And if your eyes land on the red, you lose. Okay? So those are the rules of the game. So let me recapitulate. You have to stare at the green dot. Your go signal, the signal to move now is the disappearance of the central dot, and then you are able to move your eyes. If you're lightning fast and your eyes land on the gray, you're okay, you make 1 point. If your eyes land on the green, you're mean, That's the best possible outcome. If your eyes land on the yellow, you're still mellow and get 1 point. But if your eyes land on the red, you're dead. Okay, you lose. So those are the priorities. So now let's do it a little bit faster. It's something that approaches the experiment in real time. So remember, keep your eyes locked on the central green dot for a little bit. Wait until it disappears, but don't wait too long to respond because otherwise you will lose. Okay? And do not worry about finding the green dot. Let just your brain do the work. Okay? Here we go. Be ready. Okay. So this is probably faster than you expected. Okay. So actually, why don't you show me who landed on the red? Okay, so thank you. Yeah. So, all right. So quite a few of you. This is simply because it's really, really fast. So now that you know how it goes, let's do it once more for real. So this is the one that counts. Okay. Let's do it again. Stare at the green dot. Keep your eyes locked on it. And as soon as it disappears, move to one or the other side. Here we go. Okay, that probably was better. Let's see, who of you think that you landed on the green? Okay, that's pretty good. I think that's more than half of you. And that just goes to show that even though this is extremely fast and part of it you're just unaware of, essentially, your brain has enough time to take in the green and yellow information and inform the rest of your brain to move your eyes to the correct location, to the location of the highest value. So this gives you an idea of these urgent choices. Now, it may seem a little bit contrived. Okay, so this is a sort of a simplified video game, but why do we care about it? Well, a lot of us like these urgent choices a lot and may even pay a lot of money to go watch them in real time. I'm talking about sports. There are a lot of situations in sports in which this exact same conflict occurs all the time. You have to move really, really fast, and you have to adjust your motion plans on the fly on the basis of just a glimpse of visual information. So there are lots of examples in sports where this is true, but the best one probably is the case of soccer. So if you ever watched a game of soccer, in particular penalty kicks, you may have noticed that the goalie stands there and typically jumps way before the striker hits the ball. Sometimes this is kind of comical. He jumps to the completely opposite side where the ball is going, like here. But some other times, he guesses correctly and he puts himself in a position to be able to deflect the ball. So that's the essence of the conflict. This is a good strategy for the goalie, because if he stood there and waited to see where the ball was coming from, was going to, then he would not have enough time to respond. He would always miss it. In this way, by guessing and making an early start to his movement, he puts himself in a position to get a 50% chance of deflecting the ball. So that's the essence of the conflict. So there are two ingredients that are going on here: an early movement plan and the adjustment of that plan on the fly when visual information becomes available. Okay, so those are urgent choices. Now, what have we learned by studying these kinds of choices? Well, we have learned essentially three things. The first of them, the first thing is just generally about their timing. When I tell you, look now, move your eyes now, it takes you about 250 milliseconds to do this, about a quarter of a second for you to be able to actually start moving your eyes. But if we present the green and yellow for just a little bit longer, 150 or maybe even 130 milliseconds, then you're able to reliably tell which one is where. So 50 or 30 milliseconds is the difference between knowing exactly what you're doing and having no idea and just guessing. So that is pretty interesting. We've been able to clock our brain. The second thing that we've found out about that is really interesting and unexpected is that this choice process takes a particular form in the brain that looks a lot like a race. So the race here is between teams of neurons, teams of cells that produce different actions. So throughout time, and time here takes about 250 milliseconds, as I said before, throughout time, the activities of these two teams of neurons will start from a low level and start increasing until one of them reaches a finish line, a particular level of activity where an action is triggered. So this looks like this. There's a red team and a blue team. When the red team wins, reaches the finish line first, that produces a movement to the left. You look to the left. And when the blue team is the one that wins the race, that creates a movement to the right. Now, in this particular case, the situation is very simple. The red team won the race, and shortly thereafter, the crossing of the finish line, a movement to the left side, an eye movement, was triggered. And what you're seeing here is actually brain activity that we recorded in our laboratory by sampling individual cells from the brains of monkeys that are trained to perform the task that you just saw. And so by recording one neuron at a time, we assembled their activities to produce this kind of picture of how the dynamics evolve throughout 250 milliseconds. Now, this is a very simple case in which essentially the subject made a guess. There was no information to go about. He just had to choose one side arbitrarily, like the goalie. The more interesting example is the one in which the race is informed by the visual information. So that starts in exactly the same way, with the central fixation dot disappearing. That produces a little bit of activity in both racers. And again, the red team is ahead. But then comes the crucial event in the task, which is that the green and yellow information arrive to inform the circuit. So you can think of this as the color information being encoded or relayed by another team of supporter neurons that cheer for their teams. Now, because the green is on the right side, in this case, they cheer for the blue team. And so once this information gets there, it is the blue team that sprints to the finish line, whereas the red team slows down and comes back to its original level. And so what happens in this case is that the blue team wins, and therefore a movement to the right is produced. And so the subject looked at the green dot, and that was the best possible outcome. Incidentally, this is something that we call technically a change of mind. Because as you can see, the red team was ahead first, but then there was some relevant information that altered the course of the race. And we also call this an informed choice, because it was informed by relevant visual information. Okay, so that's the second important thing. Now, the third key finding about this that ties it all together is that these race dynamics are very similar to the dynamics that we think are going on during more complicated choices that occur in everyday life. So there are lots of examples, but let's talk about two of them. So the first one is the simple fact that we're all familiar with, that when the stakes are high, we typically take a little bit more time to deliberate to try to get to a better outcome. So for instance, when somebody asks you, "Are you free on Saturday?" You say, "I think so, but let me check my calendar first." Well, what you're doing is just buying time to gather more information before you commit. So, that simple example, turns out we have a very similar dynamics in the race for, the eye movement. So when we raise the stakes in our experiment, and we do this by making the value of the green dot much larger, 10 points instead of 2 points, then the subject knows that this trial is going to be really important. And what happens is that the two teams of racers slow down, both of them. They reach a sort of gentleman's agreement that the best possible outcome is to just wait a little bit longer for the visual information to get there. So instead of 250 milliseconds, let's say, it will take maybe 300, a little bit more. But that increases the success rate of the trial. Now, you would be absolutely unaware that any of this is happening because it's just completely automatic. But it does, and it does take the same type of adjustment as in real life. The other example that it will be interesting for us to consider is that of a different kind of choice that has a somewhat different flavor, but can also be represented by a race with just one team that needs to reach the finish line or doesn't. And I'm talking about choices in which you have to do something or not. For instance, a batter in baseball, every time he sees a pitch coming, he has to decide whether to really swing hard at the ball or not. And there are all sorts of temptations that fall into this category as well. Should I eat that delicious piece of chocolate in front of me or resist? So let's talk about one particular example. This is the story of Harry, a software developer that works for company M, and he's very happy there. But one day he learns that company G is hiring, and this plants the seed of an idea in his head: maybe I should quit. Now, this idea is represented by the activities of a team of neurons, the purple neurons here, that just start increasing their activity a little bit when this knowledge comes about. Now, Harry's contract is reviewed every year, and it is at this point in time that he starts thinking more about this idea of quitting. So during the first year review, the idea gathers a little bit of momentum, but then it comes back down because quitting is very risky, and the difference in pay is not worth it. Come the second year, this idea gets stronger because the difference in pay is larger now. But he's promised that it is very likely that next year he'll get a raise. So then, again, the idea subsides. The activity of this team of neurons comes back down. The third year comes by. The raise does not materialize. There were budget cuts all across the board. And furthermore, company G is hiring. And so this knowledge propels this team of neurons to increase their activity towards the finish line. And it is at that point that the decision is actually made. Harry quits. Now, we haven't done this experiment. We haven't recorded the activity in the brain of anybody that's trying to consider quitting their job. And furthermore, this takes typically a very long time. But very clever experiments with monkeys have been made that present the exact same dilemma. Either stay and face diminishing returns, or take a risk and leave to seek a better opportunity. And it turns out that we have every reason to believe that the process that I just described in the brain takes pretty much this form, that of a race of a team of neurons towards a finish line. Very good. So life is chock full of choices, difficult ones. Some of them are very fast and take under a second. Some of them may involve a few minutes of agony, like when you really want to eat that marshmallow, but you know that you're better off if you wait. Some other choices, like deciding to get married, sometimes are really very long. Take years to resolve. But what is amazing is that there are mechanisms in the brain that are the very same ones that participate in resolving these kinds of conflicts. There are some common principles whereby neural circuits perform computations for deciding which alternative is the best. And all of those principles are the same ones, regardless of the time scale, from milliseconds to years. Now, going forward, you can see that this provides us with a framework, a logical basis, or a logical setup from which we can begin to study a number of problems that are related to everyday choice. For instance, why do we sometimes take unnecessary risks? Or take impulsivity. Why is it so difficult to avoid bad choices that in retrospect were a really bad idea from the beginning? Or let's take instant gratification. Why do we have such a hard time waiting a little bit longer for a larger reward in the future rather than having a smaller one right now? So, people often ask me and tell me, this is fascinating stuff, but how do I contribute to this, or how do I participate? Well, you should know that this groundbreaking research is almost exclusively funded by the US government through fiercely competitive grants. So it is funded ultimately by you as a taxpayer. So you do contribute to this investigation into the depths of human decision making with your votes come election time, with letters to your representatives, or maybe just with conversations, informal conversations amongst friends about science. And so your position on this is important, and that is your choice.